Audible now? Is it audible now? A very good morning to all of you. Very good morning to all of you. Good morning. Good morning. So I believe that you guys are revising what we have been doing in the previous class. That was a preliminary introduction to atomic structure. Okay, good one. Very good. So we'll do what? We'll begin with certain questions regarding some isotopes, how to find out the average atomic weight. And I hope you all know that. If suppose if there's an element, say X, and whose mass number is suppose say 40 and this is say 20, what will be the atomic weight? What will be the atomic weight of this element? Come on. No, atomic weight. Atomic weight will be this thing. Weight of an atom. Weight of an atom is because of neutrons and protons. Are you getting it? This number shows you only number of protons. So atomic weight will be the weight of an atom. An atom do contains in its nucleus both neutrons and protons. So total number of neutrons and protons will be its mass number, which will also be in terms of unit. 1 unit, if you take the weight of proton and neutron as say 1 unit each, in that case it will be 40. Suppose if I have got say X element and whose mass number is suppose say 52 and let's say 26. So its atomic weight will be, come on, 52. That's good. This is atomic number. This is atomic number. This is actually mass number. So mass number will be the atomic weight. Okay, are you getting that? And if I take the mass of 1 neutron and proton as 1 unit, are you getting it? All of you getting it? Great. Chali, so let's begin that. So a question is there for you people. There is an element X. An element X is there, who has got 3 isotopes. It has got 3 isotopes whose atomic weights are 10, 12 and 14 respectively. 10, 12 and 14 respectively, and their percentage abundance in nature. Their percentage abundance in nature is 80%. This will be like say you can take 15% and this will be 5%. So you have to find out the average atomic weight of this element X. The question says that we have an element X which exists in 3 isotopes, in form of 3 isotopes, 10, 12 and 14. What are these? Basically, these are the atomic weights of the respective isotopes, and the percentage abundance which you find in nature is 80%, 15% and 5% respectively. Okay, so you have to find out the atomic weight, average atomic weight of this element X. So how you will do it? How you will do it? So average atomic weight will be basically, if you take, let's say, total number of atoms present are like say overall 100. So in that case 80 will be this one, 15 will be this one, and 14 will be, sorry, 5 will be this one. Are you getting it? So can I find out the total weight? Total weight will be 80 into 10. 10 is the weight of one atom. There are 80 of them. There are 80 of them. Total weight will be 80 into 10. Similarly, if I have weight of one atom of this part as 12, the weight of 15 will be 15 into 12. And similarly over here it will be 14 into 5. This is the total weight if I take 100 atoms of X. Are you getting it? Now average will be divided by total number of atoms found. So when you will do the calculations, you will find it to be 10.5. So I hope that you will be able to do if they give you further any other question like that. Are you getting it? Yes or no? Can you handle that? So if I give you a sample question again like this, that there is an atom Y is there, or element Y is there, and whose isotopes are like say Y1, Y2 and Y3. Okay, and their percentage abundance is say X1, X2 and say X3. So what will be the average atomic weight? Average atomic weight, come on, it will be y1 into x1 plus y2 into x2 plus y3 into x3. And since this is they're all percentages, so the total percent will be 100. So divide by 100. It will be that easy basically. Is that okay? Okay with that? Very good. Very good. Okay, great, great. So let's do one more question, I mean, for the sake of practice. And this question is like, say, we are having an oxygen atom, 16 and 8, whose mass number is 16 and atomic number is 8. And the question now says that if number of neutrons are halved and number of electrons are doubled, then find out the percentage, find percentage change in atomic weight of oxygen atom. Come on. If the number of neutrons are halved and number of electrons are doubled, find percentage change in atomic weight of oxygen atom. Come on, do it. See, 1.29. Okay, that's good. Trishal, very good. Very good. So we got one answer. It's pretty good. Okay, now look over here. See. So we all know that atomic weight is because of total number of protons and neutrons. So in O, 16, 8, I know number of protons will be 8. That will be the atomic number. Number of neutrons will be what? A minus Z. We have seen in the previous class. That will be 8. So initially the total weight will be what? 16 units. It will be 16 units. Now, what the question is saying that if the number of neutrons are halved, but protons remain same. Proton will be same. They are not changing the number of protons. Okay. So protons will be same. And now neutrons will be how much? They become half of it. There are 8 initially. Now it will become 4. So it will be 12 now. So the weight of oxygen atom is 12 now. Now they are also saying that number of electrons are doubled, but we know that the weight of an electron is negligible in front of us compared to protons and neutrons. You remember that or not? That weight of a neutron, which is almost equal to weight of a proton, is almost equal to 1837 times that of the weight of the electron. Are you getting that or not? So this can be easily neglected. This weight can be easily neglected while counting the total weight of an atom. So this is 12 now. So originally we are having weight as 16. Now the weight is 12. So decrease in weight will be how much? 16 minus 12. That is equal to 4. And if they are looking for percentage is always done on 100. So percentage decrease in weight will be how much? The decrease 4 into 100 if you want to find out percentage, and upon the original weight. Percentage is always done on the original. Remember that? So 4 divided by this 16 will be 4, and that will be 25. So it will be 25%. 25% decrease. So weight will decrease by 25%. Is it okay? Okay? Yes or no? Great, good, very good, very good, very good. Chalo. Let's do one more question. I mean, like say we are having an element X again, and I'm saying that number of neutrons are, like say, doubled. They are doubled, and number of protons, they are halved. And I'm giving you this element X as, say, again you can take like say 16 and 8. Let's take oxygen only, let's take this oxygen, I mean. So find the percentage change in the atomic weight. Number of neutrons are doubled and number of protons are halved. So what will the percentage change? Increase or decrease or what? So let's take now initially. So initially it is like, say, weight is how much? It is 16. Are you getting that? Now finally, number of neutrons will become what? 16 they will become double. They're 8 right now, and protons will be halved. Half means 8 will become 4. That total will become how much? 20. Are you getting it? Initial weight is 16, final weight is 20 units. So the increase in weight will be equal to 20 minus 16, that is equal to 4 units. So percentage increase in weight will be what? How much increase? 4. Upon what? The initial 16, and that will be multiplied by 100 if you want to calculate percentage. Okay. So 4 and 4 gone, this will be 25% again. Are you getting it? So percentage increase will be 25% increase. So can you handle these questions? Yes or no? Good one. Very good. Very good. Sorry now. Now let's come to the next topic, and this is basically electromagnetic radiation. Electromagnetic radiation. Clear? So, I mean, if you remember that last time when we were discussing Rutherford's model, according to Rutherford, this is the nucleus. An electron will be revolving around the nucleus, okay, and centripetal force will be balancing the centrifugal force. Now, this model was refuted by Maxwell's electromagnetic theory, if you remember that. Remember that or not? Electromagnetic theory. According to Maxwell's electromagnetic wave theory, if a charged particle will accelerate, revolve, or rotate, it will keep on losing the kinetic energy and will eventually fall into the nucleus. In this case, for example, are you getting that? Now, where is this kinetic energy being lost? What is happening? If a charged body accelerates, it will lose its kinetic energy. Why it will lose the kinetic energy? Yes, in the form of radiation. That is correct. Actually, Maxwell was trying to say that whenever a charged body is accelerating, whenever a charged body, it can be electron or proton or anything, any charged body, whenever it is accelerating, it will keep on radiating electromagnetic radiations. Are you getting that? It will keep on radiating electromagnetic radiation in the form of waves. Correct. In the form of waves. So that all these electromagnetic radiation, they contain some energy, and this energy, total energy, is the energy which is being lost by the accelerating particle. Is that clear? Is that clear? So we'll write down this stuff now. So what are electromagnetic radiation? Please write down. Whenever a charged particle accelerates, whenever a charged particle accelerates, it produces electric field and magnetic field. It produces electric field and magnetic field, which are transmitted in the form of electromagnetic radiations, or you can simply say electromagnetic waves continuously. So whenever a charged particle will be moving, or accelerating, it will keep on producing electric and magnetic field, and which will be transmitted in the form of electromagnetic radiation or the waves continuously. Is that okay? Is that okay? Now, few more things regarding this electromagnetic radiation. Okay, just few more things. This electromagnetic radiation, if I talk about, they contain energy. Moreover, I mean, this electric field is perpendicular to the magnetic field. Understand? And they both are perpendicular to the direction of propagation of wave. of wave. Now, what is the meaning of this stuff? Understand that also. So what I'm trying to say is that suppose we have got a charged particle which is accelerating in this direction. Now the electric field, suppose I'm saying that electrical field is propagating vertically. Vertically, are you getting that? This is the electric field. This is the electric field. In that case, the magnetic field will be propagated horizontally. I mean, this wave is moving, electric wave is moving this way. In that case, magnetic field will be moving in the horizontal plane. Are you getting that? Like this, something like this. This yellow one. So if I'm saying that, suppose this is the electric field in the vertical plane. In that case, this yellow one will be the magnetic field. I hope that is clear now. This yellow one will be magnetic field. So if the electrical field is vibrating in the vertical plane, the magnetic field will be vibrating in the horizontal plane. Are you getting that? And they both are perpendicular to this line. One up, one horizontal. Is it clear? One up, one horizontal. And this wave is moving in the vertical direction. Are you getting that? Is that okay to all of you? Now I want you people to write down one very, very important thing. All electromagnetic radiations have same speed in vacuum, or you can say in air, which is equal to how much? 3 into 10 to power of 8 meter per second. 3 into 10 to power of 8 meter per second. Moreover, electromagnetic radiations or electromagnetic waves do not require medium for their propagation. For example, if we look at the water waves can move in the medium of water itself. If there is no water, there will be no water wave. If we talk about sound, I mean, if there is no air, there will be no sound. If there is no medium, there will be no sound whatsoever. If you talk in vacuum, other person will not be able to hear you. But with these electromagnetic radiations, we don't require any medium whatsoever for their propagation. They can propagate in the vacuum also. And in the vacuum, their speed is this. Are you getting that? Come on, that's one good. Now, electromagnetic spectrum. Who will tell me how many types of radiations will be there? Come on. In this electromagnetic spectrum. First of all, tell me, what do you mean by spectrum? What do you mean by spectrum? Like if I talk about spectrum, it is basically arrangement of all possible kind of radiations, in the increasing or decreasing order of the frequency or the wave, or the wavelength. Yes, correct. So if you are able to arrange all the electromagnetic radiations in terms of increasing frequency or decreasing wavelength, or decreasing frequency or increasing wavelength, that arrangement will be called an spectrum. Okay, so let me show you something over here. So if we look over here, like this will be, like say, gamma rays. Here we have got X-rays. Here we have got UV rays. This region, I'll call it as visible region, or say visible light, which you're able to see. This will be infrared region. This will be This will be gamma, X, UV, visible, micro. Yeah, this will be microwaves, and this will be radio waves. This will be radio waves. Sometimes, I mean, you have got beyond this also, which we call it cosmic radiations, है ना? Cosmic radiations. Cosmic radiations, okay? Now, what is happening around here? If I'm moving from here to here, I have arranged them. I have arranged them in the decreasing order of their frequency. In the decreasing order of their frequency, okay? And if I'm looking over here, if I'm moving here, they are arranged in the increasing order of their wavelength. They are arranged in the increasing order of their wavelength. Is that clear? So please learn this order. This is very, very important order. You know? Sometimes they ask you direct questions and sometimes they ask you indirect questions. Like they can ask you which of the following, gamma rays, X-rays, UV rays, infrared, micro, or radio, which has the highest frequency. So the highest frequency will belong to the cosmic rays. If this is not the option, in that case, it will be like, say, gamma rays. Are you getting that? So this order is very, very important. Just go through that. Very, very important order, okay? And if they're looking for which will have the highest wavelength, in that case, radio waves will have the highest wavelength. We'll learn a little bit more about the frequency and wavelength in a short while, okay? Is that clear? So have we gone through it? Have we gone through it or not? So come on, can you learn with me right now? Can you learn with me right now? Which one? Cosmic rays the highest frequency, and in the decreasing order then? Keep writing, keep writing. Keep throwing your answers. Come on. Gamma, X-rays, then UV rays, visible, very good, then infrared, then micro, then radio waves. Is that clear? That is good. That is clearly good. So it's like that. If I'm looking at basically the wavelength, and I'm moving from here, like say gamma rays to X-rays to UV rays and to this visible light, visible light. Then we have got infrared rays, microwaves, and then radio waves, You will see that if I talk about basically their wavelength. So over here, the wavelength will be very short. And as I keep on moving over here, the wavelength increases. Here it increases furthermore, more, and like say it will be even more. So as we move away from gamma rays to radio waves, the wavelength is increasing. Is that okay? Is that okay? So if I'm able to squeeze the radio waves, if I'm able to squeeze radio waves over here, I can make a radio wave into a gamma ray. Or I can squeeze a radio wave into, say, visible rays. Yes or no? All we need is an instrument to convert this thing. Like say, so when you have radio waves and like you want to see them, you need basically a television. You need a television. So television contains, like a tool which can convert radio waves into visible rays. Are you getting that? Earlier days, they used to have like say antenna was there, and through this antenna, they used to capture, like say, all kind of broadcast. So you will be tuning or arranging the antennas in the earlier days to catch the signals properly. These signals, they were like say radio waves, and your television set-top box was able to convert all these radio waves into what? Visible rays. Are you getting it? So if you can convert them or interconvert them, you can also watch UV rays as such. You can watch infrared rays also. Remember that or not? We can't see the infrared rays, but suppose if there's a terrorist, who is roaming in the jungles out there. Are you getting that? But the thermal, the range of this person, human being, is different from the trees around. So, our naked eyes cannot see them. But, a plane flying up there or a drone flying up there, which is having an infrared reader. In that case, he will be able to see the thermal variations on the ground. Yes or no? This human being will show the blue color, maybe, in that infrared reader, and others will be like, say, maybe like, say, something else. So immediately you will come to know that, this is something different, and you can shoot them from the air itself in the night. This is called night vision. Okay. Are you getting that? So we'll be learning more about them later on. Okay. So we have in native cell. What is that? Okay, anyways, I mean, so again, coming back to this part, so let me tell you something even more important over here. So this though you must have gone through. Like they'll ask you one very important question, bache na, that what is the range of the wavelength for the visible light? Like this is basically, if you look at that Vibgyor. So since I told you that if we move from left to right, over here, in that case, the wavelength will keep on increasing. Now, what is the range? This violet basically is at the range of say 4,000 angstrom, and it keeps on moving here there, keeps on moving, and the lambda keeps on increasing. And at red, it is like say 7500 angstrom, or 7,000. I mean anything. Don't worry at all. I mean in NCERT it is written as like say 4,000 to 7,500. I mean in some books it is like say from 4,000 to 7,000 also. It depends. Don't worry at all. So roughly, I mean you can take this range as the visible range. Will that be clear? Will that be clear to all of you? Okay. So just remember this range. This is very, very important. Okay. So let's do a question now. If I ask you that which electromagnetic radiation has highest frequency? First option I'm giving you X-rays. Second I'm giving you UV ray. Third I'm giving you infrared rays. And fourth I'm giving you red light. Which has the highest frequency? Come on. In this case it will be X-ray. But if I put like say gamma ray in this as well, in that case answer will become gamma ray. Is that clear? And if I change the question to which has the highest wavelength, in that case what your answer will be? Highest wavelength, infrared. Yes or no? Yeah. So it will be like say Vibgyor, and then will come infrared. Are you getting it? And from above this, it will be ultraviolet. This is visible region. More than violet will be ultraviolet. Less than that will be called infrared. Okay? Got it? Okay. So we can move on now. Now let's do certain characteristics of electromagnetic radiation. Please write down characteristics of EM waves. Like they are for, in general, for any kind of wave. Okay. The first one is wavelength. It is written in the Greek alphabet called lambda. So what is the wavelength? If you look at basically any wave, you will see that it contains some highest point and some lowest point, above and below the line of propagation, of the wave. So this highest point is called say crest. This will be called trough. This will be crest, and this will be again trough. Now wavelength as defined as basically it's the distance between two consecutive trough or consecutive troughs or crest. So this distance between two consecutive trough will be called lambda. This distance between two consecutive crest will also be called lambda. This distance is same basically. So we can write down what is wavelength. It is the distance. Between two consecutive crests or troughs. Consecutive crest or troughs. Okay, that will be called lambda. For the sake of definition, Now there is a second term called frequency. New. And what is frequency? Suppose this is the point, and I'm referring to this point, and wave is coming. A wave is coming. Now from this point, in 1 second, how many wave cycles will pass? Now what is a wave cycle? Wave cycle is basically one complete formation. I mean, you begin from here. This will be called one wave cycle. This will be called second wave cycle. Are you getting that? Actually, if I look at that, this part, one crest and one trough, and if you combine that, that will be called one wave cycle. Is that clear? So, what is frequency? Frequency is that through a point in 1 second, how many wave cycles will pass? Suppose through a point, 5 wave cycles are passing in 1 second. What will be its frequency? What will be its frequency? Come on. 5. If through a point, like say 20 wave cycles are passing in a second, its frequency will be 20. Great. Very good. Very good. Anna. So let's write down definition as well. It is the number of wave cycles passing through a point. Passing through a point in a second. In 1 second. In 1 second is called frequency, and like say its unit will be say hertz. Its unit is hertz. Is that clear? And frequency is sometimes also called 1 upon time period. 1 upon time period. Okay. In that case, you can see that frequency will have a unit of per second also, or per unit time. Per unit time. Acha, one more thing, beta, I mean, I wish that you should be learning is that certain units will be required, beta, over here. Na? So what is 1 angstrom? Since this is light, this is electromagnetic radiations, their wavelength will be very, very small. Na? So we'll be measuring in terms of angstrom. Na? So 1 angstrom is 10 to power of minus 10 meter, or which is 10 to power of minus 8 centimeter. Okay. Similarly, 1 nanometer will be 10 to power of minus 9 meter or 10 to power of minus 7 centimeter. We should all know this at least. This is very, very important. 1 picometer is 10 to power of minus 12 meter, or you can say 10 to power of minus 10 centimeter. Examiner can give you anything and can ask you anything. So at least we should be very well versed with the conversions of the units. Okay. So just learn that, very, very important, and keep on revising if you are not very well versed with that stuff. Sure? Done? Okay. So then there is basically new bar, and that is called wave number. That is called wave number. Now, what is wave number? What is wave number? So suppose that we are having, suppose say a wave cycle, and this obviously will be what? The wavelength. This distance will be called wavelength. And this lambda is suppose say 10 meter. Suppose say 10 meter. Okay. In that case, wave number is number of wave cycles. Number of wave cycles in 1 unit. 1 unit will be, if this is meter, 1 unit will be how much? 1 meter. Suppose this is 1 meter. Are you getting it? Are you getting it? It is the number of wave cycles in 1 unit length. In 1 unit length. And that is called wave number. It is number of wave cycles. Number of wave cycles in 1 unit length. Are you getting it? So in this case, if the lambda is 10 meter, I mean, are you getting it? So how many wave cycles will be there in 1 meter? How many of them? 1 by 10. 1 wave cycle is in 10 meter. 1 wave cycle is in 10 meter. In 1 meter, how many wave cycles will be there? 1 by 10. Yes or no? It is the number of wave cycles in 1 unit length. If the wavelength is 10 meter, how many waves will be there in 1 meter? Come on. One by 10. 1 by 10. Good. Very good. Very good. Very good. So, I mean, if you look at that, this will be equal to 1 upon lambda, 1 upon lambda, and its unit beta will be like say per meter or say per centimeter, depending on that. Is it clear or not? If lambda is in meter, it will be per meter. So be very clear with that stuff. Okay. Then the last one is called amplitude. So what is the amplitude? If suppose I'm talking about one radiation, the maximum distance from the line of propagation is called amplitude. This will be called amplitude. Are you getting that? Last slide. Okay, here we go. Done? Okay. You can just note it down, I mean, later on. Surya, I'll be giving you this code for that, and you can just ensure that you are getting all of that from this code, okay? So please, but don't disturb the flow. Let the class flow, okay? So this will be called amplitude, right? And remember that there is something called intensity. Intensity, which is nothing but actually brightness, right? Brightness, they are actually proportional to amplitude square. Amplitude square. According to what? According to what? Electromagnetic wave theory. According to electromagnetic wave theory. A lot you will learn about electromagnetic wave theory. Hi, in YouTube, this class will come. Don't worry at all. Na? So according to electromagnetic wave theory, intensity of the light or the brightness of the light is proportional to the amplitude square of the given wave. Okay? Is that clear or not? So this electromagnetic wave theory was able to explain many things, and I will come to that part also. But before that, let's do few questions, I mean. Okay, shall we do the questions? Few questions, I mean. So I'm giving you this, all these questions are for electromagnetic radiation. All of them are for electromagnetic radiation. So first one I'm giving you is that if lambda is given as say 5000 angstrom. So can you find out the frequency? Can you find out the frequency? Come on. Find the frequency. Now, to do this question, I mean, you should be able to understand one thing, that what is the relationship between lambda and frequency? What is the relationship between lambda and frequency? We all know that all these electromagnetic radiations, they travel with the speed of light. And this speed of light is actually lambda into frequency. Lambda into frequency. Are you getting that or not? The C is equal to lambda into frequency. So that I can say that frequency will be equal to C upon lambda. C upon lambda. Also I can say that from here, since C is a constant, the speed of light is constant in a given medium. So frequency is inversely proportional to lambda, which actually means that if frequency will increase, in that case, lambda will decrease, and if frequency will decrease, in that case, lambda must increase. Lambda must increase. Yes or no? And C is equal to how much? 3 into 10 to power of 8 meter per second. Okay? Chalo aa jao. So if lambda is equal to 5000 angstrom, what will be the frequency? Yes, we know that frequency will be C upon lambda. So C is 3 into 10 to power of 8 meter per second. Are you getting that? And lambda is given as 5000 angstrom. This is meter, this is angstrom. The units are not matching. So what you will do? You will try to match the units. So convert angstrom into meter. So you will do what? Multiply by 10 to power of 10. 10 to power of 10, because I know that 1 angstrom is equal to 10 to power of minus 10 meter. So this will be a conversion I'll use over here. So once I use it over here, I can see that this will be gone. This will be 10 to power of minus 7. This will go up. So this can be like say 3 upon 5 into 10 to power of 15. I can rearrange it 30 into 10 to power of 14 upon 5. So 5, 6. This will be 6 into 10 to power of 14 hertz. Is that clear? 14 hertz or 6 into 10 to the power of 14 per second. Is that okay? Okay. Let me have some water. Shall we? Then there is a question basically in the NCRT, which I believe everyone should be able to do it. It says that Vivid Bharati radio station, hai na? So I'm saying that a radio station is broadcasting at frequency equal to 1368 kilohertz. This thing, find lambda of electromagnetic radiation. Find the lambda of electromagnetic radiation. You have to give the answer in meter. Who will give the answer in meter? Come on. Is broadcasting at the frequency of 1368 kilohertz. Chalo, theek hai. Now we all know that all electromagnetic radiations will travel at the speed of light, and if nothing is given, we'll assume it to be in the air or vacuum. Now I know that C is equal to lambda into frequency. They want lambda now. Lambda will be C upon frequency. Hai? Make sure that you are matching the units as well. 3 into 10 to power of 8 upon frequency 1368 kilohertz. Hai? Now what he will do? Convert this kilohertz into what? Hertz. I know one thing, that 1 kilohertz is equal to 1000 hertz. So multiply by 1000 to convert kilohertz into hertz. Yes or no? So once you do that, this will be gone 10 to power of 5, and for the sake of simplicity, we can say that this will be 3000 into 100. I can write down 10 to the power of 5 as 1000 into 100, 1368. Like this will be like now almost 2 point something. This will be like say 219.3. If you see that 2 point something multiplied by 100 will be 200 something. And exact answer is 219.3 meter. Is that okay? Is this calculation okay with all of you? Please do it. I mean, this is a very famous question. This is normally asked. I hope you can handle these questions now. Will it be okay? Good one. Very good. So I'll just say that I'm keep on doing NCRT, keep on reading NCRT, and if you have got any doubts whatsoever, please do feel free to ask any of your doubts. We are here to solve your doubts. Okay, come on. Now, I mean, this electromagnetic wave theory was able to explain many phenomena successfully. So, for example, this electromagnetic wave theory given by Maxwell was able to explained successfully, for example, certain phenomena like diffraction, interference, polarization, okay, this they will teach you more in the physics part, don't worry at all. But this theory was able to explain diffraction, interference and polarization. But there were certain phenomena which were like say discovered in the beginning of the 20th century, which electromagnetic wave theory was not able to explain. Now the fact is that students, that when you have a theory is being put forward by human beings, and we are not gods. We are just trying to understand the creation. the nature, the universe. So while I'm trying to understand that universe, the phenomena which is occurring in the universe, we begin with certain assumptions sometimes. So these assumptions may or may not be right. Now, to verify whether the assumptions are right or wrong, we do perform some experiments. So if our theory is able to explain the experiment, that means our theory is correct. It's okay, keep on moving forward. But suppose if your theory is not able to explain the experiment, or the assumptions or the postulates you have been putting forward are against the experiment, experiment is not wrong. Experiment does not give you wrong data kind of thing. This is correct. This is observed. You have to explain. That means you have to change now. So that's the journey of science. We begin with certain assumptions, keep on verifying with the help of experiments. Whatever the faults are there or deficiencies are there, we try to overcome them, okay, emerge from them and rectify them. And this way the science keeps on moving. Okay. Okay. So, I mean, when these were, like, say, explained beautifully, like, scientists were very happy that they have given a very good, wonderful theory which is able to explain some very, very complex phenomena. But in the beginning of 20th century, as I told you right now, they were not able to explain certain phenomena. So let's discuss those failures of electromagnetic wave theory. Okay. So failures of electromagnetic wave theory. The first phenomena which couldn't be explained by EM wave theory was black body radiation. Very good. Black body radiation. Second one was photoelectric effect. Third one, come on. Spectrum of atom. And fourth one is also there. What is that? Who will tell me the fourth one? Though this is not in syllabus in detail as such. Okay. That is what? Heat capacity change. Heat capacity change of solids with temperature. With temperature. Of these four, basically, these are the three which are most important, and we'll discuss them in detail in this chapter. Okay. So let's begin with the first thing first. The first thing is black body radiation. Black body radiation. So first of all, what is a black body? So black body is a perfect emitter and absorber. Emitter and absorber of all kind of radiation. Any body which can perfectly emit and absorb all kind of radiation will be called a black body. Sometimes people do confuse with black body with black hole. Black hole is something different. Black body is totally different thing. Okay. Black hole is something which, I mean, from which even light cannot escape. Are you getting it? It simply absorbs. But now there are certain changes coming in the definition of black hole at higher level, but we shouldn't be concerned with that. Okay? So black body is a perfect emitter and a absorber of all kind of radiation. Now, since perfection doesn't exist as such, so this is basically a concept. It is an ideal body. And like, since it doesn't exist, a very near example we can take will be basically what? You can take a vessel basically with a pinhole into it. So whenever any radiation will move over there, it will keep on bouncing until this radiation comes in thermal equilibrium with the surroundings as such. So black body is a body which is in thermal equilibrium with the surrounding. What is the meaning of that? It means that it will be absorbing and emitting all possible kind of radiation. That means amount of energy absorbed will be equal to amount of energy emitted. This is the meaning of any body which is in thermal equilibrium with the surroundings. Black coated, ball, no, it's like it's a ball coated with the platinum black and a small hole in that. So it will keep on moving till it becomes or comes in the thermal equilibrium as such. Are you getting it? With the surrounding itself. And there will be no possibility of this thing coming out as such. Okay? Chalo, aa jao. Now, I mean, like, what was happening with this black body which electromagnetic wave theory was not able to explain? So actually, when the scientists were doing experiments, they plotted the graph of intensity and wavelength. The graph which they saw or were observed was something like this, okay? But according to electromagnetic wave theory, the graph which they got was this. Now their theory gave this graph while the experiment was giving this graph. The theory was not able to explain the graph. That means something was wrong with the theory. This graph was never coming down whatsoever. Are you getting that? Okay. According to electromagnetic wave theory, if there is any body out there, anything which is like emitting radiations, I mean, it will emit infinite radiations, I mean. That means a lot of infinite amount of heat energy or energy will be radiated, which is not the case. According to EM wave theory, any hot glowing object was considered as a black body, which was incorrect, because according to them, any hot glowing object will emit all possible radiations and all possible radiation. That means this hot body, which is glowing body, for example, if I take, like, say, red hot iron, if I take red hot iron, in that case red hot iron will be emitting even infinite amount of gamma rays also. Like, gamma rays are having very high energy and you all will be killed if you are in the vicinity of a red hot glowing iron object, which is not the case. That means certainly something was wrong with the electromagnetic wave theory and their assumptions. So let me first explain this graph, what this graph is all about. So when you will be observing this graph, you will find that this is intensity, the brightness, and this is, say, lambda. So graph is something like this. This graph is at, say, 5,000 degrees Celsius. This graph, second graph, is suppose, say, 7,000 degrees Celsius. That means for the yellow line, the temperature is slightly higher. I'm assuming that. And for the white line, this graph is at 5,000 degrees Celsius. Now, what I'm trying to say is that, suppose when you take iron and when you start heating that, you will see that initially it becomes red glowing object. It becomes a red glowing object. After some time, it becomes like, say, a white glowing object. And if you even give more heat, in that case, finally it will become like, say, blue glowing object. So what is the meaning of this thing? What is the meaning of this thing? That if an object is glowing red, do you mean that it will be emitting only red radiations? Only red radiations? No. It will be emitting, I mean, suppose it is radiating all kind of radiations. In that case, 90% will be red. Maybe, say, 5% is, say, yellow. Maybe, say, 1% is, say, blue kind of thing. Are you getting that? So, I mean, if I ask you, if something is emitting all these radiations, 90% of them are red, and rest are as yellow, blue, violet, or green, whatever. So, what will be the color of the object you will observe? Blue, yellow, or red predominantly? You will see the color of this object as red. And suppose that if 90% of the radiations are coming as blue, like, say, 2% are, say, yellow, 1% is, say, green, and so on. So what will be the color of the object which you will see predominantly? Blue. That means any color you see is not the only color which is coming out of that object. It is the predominant color which is coming out of that. Are you getting it? The dominant color. So when you see something blue, it doesn't mean that it will not be emitting red light. It will be, but it will be minuscule. Okay? Very less as compared to that of blue light. Now, how this happens, bacho? If you remember that Maxwell told that whenever a charged body is vibrating, it will keep on emitting what? Electromagnetic radiations. Like, if the frequency of the vibration is more. Acha, when the frequency will be more, beta? When the temperature will be more the temperature, more will be the kinetic energy. Yes or no? We have all known that kinetic energy is equal to 3 by 2 RT, or say 3 by 2 KT if I'm talking about one particle. Are you getting that? So from here I can see that kinetic energy is proportional to temperature. More the temperature, more is the kinetic energy. So if temperature is more is the kinetic energy, more will be the vibration. More the vibration, more the frequency. Yes or no? More the frequency, lambda will be less. Lambda will be less. Yes or no? That means if temperature is less, kinetic energy will be less, frequency of vibration will also be less, and wavelength will be more. Yes or no? Now, before I move forward, you people let me know that if I'm talking about Vibgyor, you know that in this Vibgyor, over here, if I move, lambda increases, but frequency will decrease. That means violet will have highest frequency, okay, but wavelength will be least. Red will have least frequency, but wavelength will be highest. Yes or no? So tell me one thing, when the temperature is high, kinetic energy is high, frequency is high, wavelength is low, which color you will see? Violet, indigo, blue? Yes or no? Violet, indigo or blue kind of thing, hai na? Which is combinedly called like say blue. Will be called combinedly like say blue. Yes or no? And when the temperature initially is less, kinetic energy is less, frequency of vibration of particle is less, lambda is higher. So which color you will see, boys and girls? Come on. You will see red. So that's why at lower temperature you see what? Red. Because over here temperature low. You are increasing temperature. So at higher temperature you see blue as the predominant color. Yes or no? Yes or no? As you keep on increasing temperature, most particles are vibrating at blue range. At lower temperature, most particles are vibrating at red range. So yeah, that's why you will see it red in color. Yes or no? Yes or no? And this graph will be explained now properly. Do you see that over here the lambda is supposed to say increasing kind of thing? Okay? Yes or no? So as you see that over here, I'm assuming, let me change the colors so that you can at least understand red one. So I'm making it, I'll make it blue. So this is say red. This is say red. And this is says blue. This is say blue. So I'm assuming that, this is lambda, and lambda so over here, if I'm moving, lambda is decreasing, or you can say frequency is increasing. So lambda, over here I'm taking as say lambda will be decreasing in this direction. That means over here lambda is high, here lambda is low. That means frequency is high over here on this part. So you can see that at this temperature 5000, at this temperature most particles are vibrating at which color? Red color. Are vibrating at red color at lower temperature. That's why you see what? Which color? The maximum intensity is what? Red color. Yes or no? But as you increase the temperature, most of the particles are vibrating at what? Higher frequency than this thing. Yes or no? Or lower wavelength. So lower wavelength is, this is for blue. This is for say red. So most particles are vibrating at blue range or blue frequency. That's why you are witnessing what? Blue color at higher temperature. Yes or no? Come on. Tell me. Is that clear or not? Everyone getting that? The concept is clear or not? Okay, that is good. So like electromagnetic wave theory was not able to explain this. to understand this part, I mean, we have to understand Max Planck, है ना? So Planck's quantum theory. Planck's quantum theory. According to Max Planck, understand this this is very important, and that first one, his postulates. Let's talk about his postulates. So he gave some postulates, some assumption that all radiations are due to vibration of charged particles, and this can be like, say, electron or any cation or an ion, na? Okay. Secondly, all radiations have energy. All radiations have energy, whether this is like, say, UV ray, gamma ray, X-ray, radio waves, all have the energy. Third one, this energy is emitted or absorbed in packets, in form of packets, and they are called quanta. Okay, they are called quanta. Next one, energy of each packet is proportional to frequency of the vibration of the charged particle. That actually means energy of a packet or the quanta is equal to h nu, is equal to, you can say this, E is proportional to nu, E is equal to h nu, E is equal to h nu, where this nu is the frequency of the vibrational particle, E is energy, h is the Planck's constant. H is the Planck's constant. And its value is equal to 6.6 into 10 to power of minus 34 joule second. Remember the units, very important, very बच्चे, ठीक है? Okay. Now, suppose this is the energy of one packet. So, total energy of n packets. Total energy of n packets will be equal to what? Energy of one is h nu. Energy of n packets will be n h nu. E will be equal to n h nu. That is the total energy. Yes or no? And also, you know that E is equal to h nu, and we all know that for all electromagnetic radiation, C is equal to lambda into nu. That means I can say that nu is equal to C upon lambda. If I can replace the value of nu over here, it will become what? E is equal to what? H, and nu equal to what? C upon lambda. So energy can be written in this format also. This is very important, very important. And over here, remember that since we'll be doing many questions, so this H, if I look at HC, it will be 6 into 6 into 10 to power of minus 34, and C will be 3 into 10 to power of 8. So you will find at many places HC upon lambda. So this calculation will become inevitable. You cannot avoid it. So rather than writing it multiple times, I'll say that learn this value. It will make your life very easy. Approximately, very approximately, its value is almost like, say, 2 into 10 to power of minus 25. Please learn this value, and whenever you find HC, in place of HC, rather than doing it again and again, learn this and put it and get the answer directly. Is that clear or not? Okay, so come over here now. Come. And last point is that these packets of energy are transmitted in the form of waves. Are you getting that? So suppose there is a black body, for example. So black body will be radiating what? The packets of energy. Are you getting that? It will be radiating packets of energy, and each packet will have energy of what, say, h nu. But these radiation or these packets will be emitted in the form of waves. They will form a wave. Are you getting that? Or not? So earlier, according to electromagnetic wave theory, what they said, this is according to Planck, this is according to Max Planck, and according to electromagnetic wave theory, if there is a black body, it will emit radiation in the form of waves continuously, while the packets are emitted discontinuously but in the form of wave. Are you getting it? Everyone getting that or not? Is that clear or not? Okay, chalo, let's do a question now. Let's do a question. Suppose I'm giving you for electromagnetic radiation, and I'm giving you lambda is given as 5,000 angstrom. Okay, find energy of one packet or one quanta. Find energy. So you all know that E will be equal to what? Hc upon lambda. I told you that please write down this Hc as what? 2 into 10 to power of minus 25 upon lambda, which is 5,000. Agree or not? But remember that the C was 3 into 10 to power of 8 meter per second, and this is still angstrom. So convert this into what? Meter, 10 to power of minus 10. So this will be gone. This will be 10 to power of minus 7. This will be 10 to power of minus 18. And I believe this will be 4 into 10 to power of minus 19. Yes or no? Joule. Correct. Be careful with that. Be very careful. Okay. So my next question is that if lambda of the radiation is, say, 4,000 angstrom, find energy of one mole of photons. Come on. 1 mole of photons. Now total energy I told you is what? N Hc upon lambda. Will you agree with me or not? N Hc upon lambda. Hello. Okay. So this is 1 mole. 1 mole is 6 into 10 to power of 23. Hc will be 2 into 10 to power of minus upon lambda is 4,000. What I should do? Multiply by 10 to power of minus 10 to match the units. Yes or no? Now this will be 10 to power of minus 7. This is 10 to power of minus 18. This is 10 to power of 5. And 6 to the 12 divided by 4. This will be 3. This will be 3 into 10 to power of 5. What? Joule. 3 into 10 to the power of 5 joule. Yes, very good, bachu. Very good. Or not 3 joule, it will be 3 into 10 to the power of 5 joule. Check it out, Trishal bhaiya. See the calculations. Very careful. Be very careful. Is that okay or not? Come on, everyone. Come on. Similarly, if they ask you a question that we have got 3 into 10 to power of, say, 18 photons, and lambda is given as, like, say, 5,000 or say 6,000. 6000 angstrom. Find total energy. Can you find out total energy? Can we do it? Yes. Total energy will be nhc upon lambda, which will be 3 into 10 to power of 18 photons. Yes or no? And this will be how much? 2 into 10 to power of, bolo bachcho yaar, minus 25, and this will be 6000 into 10 to power of minus 10. This is gone, 10 to power of minus 7. This is gone, 10 to power of minus 18. Gone. This clear up. This is all gone. 1, that's it. Equal to 1 joule. 1 joule. Okay? That will be equal to 1 joule. Now, like say one more thing, whenever energy is given in electron volt, whenever energy is given in electron volt, lambda is given in terms of angstrom. And now, very, very important. In that case, you can write down E is equal to 12400 upon lambda. With this E is in electron volt and lambda is in angstrom. Please understand. And if, understand also, E is in electron volt and lambda is given in nanometer, in that case it will be 1240. Please learn this. This is a shortcut, so that you can easily handle these things. Okay, beta? So can I give you a question directly, beta? Come on, let's handle that. So question number 1 coming your way is that energy of a photon is given as, like say, 3 electron volt. They're saying find lambda in terms of angstrom. Come on, find lambda in terms of angstrom. Who will do it? Come on. E is equal to 12400 upon lambda. Lambda will be 12400 upon E. E is how much? 3 electron volt. So it will be 431. Okay, 3133.3 angstrom. Sorry, my mistake. This is 4. This will be 4. My mistake. 4. 4133.3 angstrom. Correct. Completely correct. So is that okay with you all? Completely? Fasak? Is that clear or not? Come on, let me know. Now, what you will do, you will just revise these things. 1 or 2 questions are left from this part. And in the next lecture, we have to cover up photoelectric effect. So we have covered up very good, very good. The speed was very good. And you guys have given really some good answers. Okay. Okay, Sam. God bless you. And this time, please keep on working very hard. And next year, we're looking for a very good result from you. This is very easy. All that spectrum of atom, no, we will not be able to complete the spectrum of atom. We'll just begin that. And in the coming test, we have the syllabus till photoelectric effect only. Okay. Surya, normally, we don't have that much of time. So motivation I'll give you. Don't worry at all. I'll definitely keep on motivating you people. But I seriously need, some speed as of now, similarly, Okay, God bless you. Take care. Bye-bye. Bye. I'll send you the QR code. Where is the QR code? Come on. You'll get it. Bye, bacho.